Good morning, everyone. My name is Palden, Tamang, roll number 21NSO-304, BSc third semester, Department of Physics, and my topic is De Morgan's theorem. Starting with content, number 1, introduction, number 2, principle of De Morgan's theorem, number 3, De Morgan's theorem, number 4, De Morgan's first law implication using logic gates, number 5, De Morgan's second law implication using logic gates, number 6, De Morgan's equivalent gates, and lastly the conclusion. About the introduction of De Morgan's theorem. De Morgan's theorem proved mathematical verification of the equivalency of the NOR and negative AND gate and the equivalency of the NAND and negative OR gates. A plus B is equals to A not B is equals to A plus B. To use the De Morgan's theorem in simplifying Boolean expression, the following algorithm is needed. Number 1. Negate each variable. Number 2. Replace dots with plus and vice versa. Number 3. Negate the whole Boolean expression. Further, let me explain the principle of De Morgan's theorem. De Morgan's first theorem. The left-hand side of the theorem represents the AND gate that has inputs A and B as we seen in the figure. On the other hand, the right-hand side of the theorem represents the OR gate that has inverted input as we seen in AND gate is equals to bubbled OR. Second, the OR gates here is known as bubbled OR as we seen in the figure 2. Now the truth table of the first De Morgan's theorem. Here is a table that shows the verification of the first theorem of the De Morgan's, which clearly satisfies the theorem. Now the second De Morgan's theorem says the left hand side of the theorem represents the NOR gate that has input A and B. On the other hand, the right hand side represents the AND gate that has inverted input as shown in the figure, that A plus B is equals to A not B nor is equals to bubble and the AND gate here is known as bubble AND as shown in the figure. Furthermore, the truth table of the De Morgan's second theorem says that here is a table that shows the verification of the second theorem of the De Morgan's, which clearly show that the NOR and NOR bubbled and OR gates. Furthermore, the De Morgan's theory. De Morgan's theory said that basically two sets of the rules or law developed from the Boolean expression for and or and not using two inputs variable A and B. The two rules or theorem allow the input variable to be neglected and converted for one form of a Boolean function into an opposite form. De Morgan's first theorem states that two or more variables not together is the same as the two variables inverted and inverted, while the second theorem states that two or more variables and together is the same as the two terms inverted or this is replace all the or operator and an operator or all the and operator with all or operator. Furthermore, the De Morgan's first simplification using logic gates. The logic gates arrays of A not B can be simplified using a NAND gate with an inputs A and B as shown in the figure. Input AB goes through process, uh, gives product A plus B is equals to A not B is equals to AND gate or A and B, which become the inputs to the OR gates. Therefore, the output from the OR gates becomes A plus B. Thus, AND OR gates with inverted NOT gates on each of the inputs equivalents to NAND gates function, and the individual NAND gates can be represented in the way as the equivalency of a NAND gate is neglected or De Morgan's second implication using logic gates. The logic gates arrays A plus B can be implemented using NOR gate with inputs A and B. The lower logic gates arrange when first inverted, the two inputs producing A plus B, which become the inputs to the NAND gate. Therefore, the output from the NAND gate becomes A, not B. Thus, AND gate will inverted NOT gate on each of the input is equivalent to NOR gate function, and individual NOR gates can be represented in this way as the equivalency of a NOR gate is negative. And through all we have used De Morgan's theorem, which only two inputs variable a plus b, they can equally valid for use with 3, 4 or more inputs variable expression. De Morgan equivalent gates. We have seen that the De Morgan's theorem replaces all of the NAND dot operator with or positive and the vice versa, and then complement each of the terms of variable in the expressed by inverting it. It is zeros to ones and ones to zero before inverting the entire function. Thus, the obtained the De Morgan's equivalence for NAND and or NOR gates. We simply added inverted NOR gate to inputs all outputs and change an and symbol to an or symbol, or change and or symbols to an and symbol, as shown in the following table. As we seen in the following table, the and symbol and or symbol change into or symbol and symbol through positive to negative or into to positive, as we seen in the table. Of De Morgan's theorem. De Morgan's law is used in both elementary algebra as well as Boolean algebra. Given below are some other applications of De Morgan's law. De Morgan's law application can be seen in electronic engineering for developing logic gate. By using this law, equation can be constructed using only the NAND and or NOR gates. The result in cheaper hardware. So, further hand NOR and NOR gates can easy to amplify partially. De Morgan's law is used in the computer programming. The law helps to simplify logic expression written in codes, thereby reducing the number of lines. Thus, it helps in the overall optimization of the code. Furthermore, this law are make verifying SAS code much simpler and faster. Lastly, the conclusion. It describes the equivalence between gates with inverted inputs and gates with inverted outputs. When breaking a complemented or NOR bar in a Boolean expression, the operation directly underneath the break, reboot, and the broken bar pieces remain over the respective term. It is normally easy to approach a problem by breaking the longer bar before breaking any bar under it. Two complementation bar are never broken in a state. Complementation bar function as grouping symbol. Therefore, when a bar is broken, the term underneath it must remain grouped. uh, Paths may be placed around this group term as a help to avoid changing precedence. So I would like to express my special thank to our subject teacher for giving us this opportunity to do this wonderful project on the topic De Morgan's theorem, which also helped me in doing a lot of research and also come to know about so many things about this topic. Thank you for everything.